Today we're going to quickly talk about modeling with sequences. We've already been through arithmetic and geometric sequences, and you should know the explicit and recursive formulas for both. One thing we haven't discussed as far as sequences go is their domain and range. The domain of any sequence, regardless of type, consists of the term numbers. We always have a first term, a second term, a third term, and so on. So all those natural numbers, all those counting numbers, will be our domain. The range of a sequence are the numbers of the sequence itself. For instance, if I have a geometric sequence with an initial value or initial term of 2 and a common ratio of 3, the numbers in the sequence 2, 6, 18, 54, and so on would be our range. There are two types of sequences, of course, arithmetic and geometric, and we're going to focus for just a second on the main differences between the two types, and that's going to help us with what we're trying to do today. In an arithmetic sequence, of course, we add a common difference to every term in the sequence, where in a geometric sequence, we're multiplying the common ratio to every term. If you haven't noticed this before, the explicit formula for arithmetic sequences is an equation that's in slope-intercept form, or can be written in slope-intercept form. So if I were to graph an explicit formula for an arithmetic sequence, it would be linear. It would be a straight line. A geometric sequence, however, if you take the time to look carefully at its explicit formula, is an exponential equation. So if I were to graph a geometric sequence, it would have that special exponential curve. An arithmetic sequence, of course, has a constant rate of change. Since it's linear, it has a constant rate of change. A geometric sequence has a rate of change that is not at all constant. Let me show you what I mean. Here I have two sequences, one arithmetic, one geometric, and I'm going to look at the difference in value between each set of terms, between each pair of terms, or sequential pair of terms. If you look at the arithmetic sequence, you can tell that every time I move from one term to the next, my rate of change remains constant. But not so with a geometric sequence. That makes all the difference with what we're doing today to decide whether we're talking about an arithmetic situation or a geometric situation. So we're going to use these differences to pull from context. We're going to be able to create equations from that context and then use those equations to solve problems. And which sequence formulas would be most efficient for our task today? That would definitely be the explicit formulas, since the recursive formulas don't actually help you solve anything. So let's give this a try. We're going to start with one section of a stadium that has 40 rows of seats. If there are 15 seats in the first row, and each row has 2 more seats than the one before, how many seats are there in the last row? First of all, take the time to pay attention to the rate of change. Since our rate of change, or the change in each row, is exactly 2 every single time, this is an arithmetic sequence. So we're going to pay attention to the explicit formula for arithmetic sequences. To solve what the equation's asking for, I need to have a value for n, I need to have an initial term, and I need to have a common difference. Well, the initial term and the common difference, that's pretty easy to find. We start in the first row with 15 seats. And every time we move to the next row, we add 2 more seats. That's our common difference. The value for n, sometimes in context, is a little difficult to find. Fortunately, in this context, it's not so difficult because we know we have 40 rows. We're looking for the number of seats in the 40th row. Now I simply need to substitute my values into my equation. And then when I solve, of course, multiplication comes before addition. So 2 times 39 gives me 78. 15 plus 78 gives me a total of 93, and we're almost done. Being able to say that a sub 40 is equal to 93 is not enough in these situations. Remember, when you're asked a question in context, you need to answer in context. I could say something like, there are 93 seats in the last row, or in the 40th row there are 93 seats. However you want to put that into a phrase. Now let's take a look at a situation where a new computer was sold for $1,000, and if the value of the computer at the end of each year is only 80% of the value of the previous year, how much will the computer be worth after 3 years? So our rate of change, 1,000 is not our rate of change, that's our initial value, right? Our rate of change is 80%. My question to you is, will 80% of the computer's value this year be the same as 80% of the computer's value next year? No, not when something depreciates. If you have a rate of change that's a percent, that is not a constant rate of change. So this would be an example of a geometric situation. So the parts that we do know, we know our initial value, we know our rate of change, 0.8 for 80%. Finding n in this situation is a little bit challenging. I'm going to explain why I chose 4 as my value for n in just a moment. Just kind of briefly, however, we have our initial value, and then the computer will have depreciated 3 different times, right, after 3 years. So we're looking for the computer's value in the 4th year, and like I said, I'll explain that more in just a second. So if I look at the explicit formula for geometric sequences, I can substitute my values into the equation. Order of operations says I have to do exponents before I multiply. And if I put this in my calculator in the right order, I should get 512. Of course, I have to explain my situation. If it's asked in context, answer in context. And I would say after 3 years, the computer is worth $512. Now let me show you a little more why I chose 4 for n. If I were to write out the actual terms of this sequence, we start with a value of $1,000. After 1 year, if I multiply 1,000 by 0.8 for 80%, I have a value of $800. After 2 years, I have to multiply the 800 by 80% again. So 800 times 0.8 gives me 640. And then I have to repeat the process, multiplying 640 by 0.8 to get the value after 3 years, which is 512. So I have my initial value, and then if I'm looking for the value after 3 years, I'm actually looking for the 4th term of my sequence. That's why I chose n being equal to 4. Sometimes if you're looking at small terms, right, one of the first few terms of your sequence, sometimes it's easier just to write out the actual terms of the sequence to answer your situation. So again, I'm looking for the 4th term. Let's take a look at one more situation. Suppose you participate in a bike-a-thon for charity. The charity starts with $1,100 in donations, and each participant must raise at least $35 in pledges. What's the minimum amount of money raised if there are 75 participants? Well, 75 participants raising a minimum of $35. $35 is going to be our rate of change, right? For every participant, we're going to increase by $35. That sounds pretty constant to me, and of course that's just a minimum amount, but that's what it's asking us for. So let's take a look at our values. And again, we're going to be really careful about the value of n. The value of n is not as important as paying attention to the context and paying attention to the situation. In this situation, we want to pay attention to how many donations there will actually be. So let's look. We know that because this is a constant rate of change, every participant's going to increase by $35 or more, I know, but remember we're talking about the minimum amount. So if I kind of tweak that explicit formula for arithmetic sequences, a sub n is our total value in this situation. A sub 1 is our starting value, our starting amount of donations. D, of course, is our common difference. And n, or how many donations I'm going to have, depends on how many participants there are going to be. So instead of just coming up with a value for n, let's focus more on that aspect. I do, however, have a definite initial donation, right, $1,100, and I know how much money, or the minimum amount of money, each participant's going to donate, and how many donations I'm going to get, or how many participants there are. Once I solve this, of course using order of operations, I get 3,725, and I can go ahead and answer the charity will raise at least $3,725. Okay, I think that's enough for today. Be really careful about what term it is that you're trying to find. Pay more attention to your context than you do in finding the value of n. For now, I'm going to wish you a great day, and of course, I'll see you next time.